This is a tutorial on rational zeros. Rational zeros are rational numbers that when plugged in for x make our function equal to 0. Or you can think of these as solutions for x. Now if all of our coefficient terms are integers, that means that all of our rational zeros, or our solutions then, are possibly represented by this formula p over q, where p is a factor of our constant and q is a factor of our leading coefficient. Now there may be other solutions to this function, but this will help us find the rational ones. It won't help us to find any imaginary numbers or anything like that, but at least we can get our rational solutions using this form. So let's practice this. Remember, it's p over q, where p is a factor of our constant and q is a factor of our leading coefficient. So what are the factors of our constant and our leading coefficient? Well, 16, we can get 16 by multiplying 16 times 1, or negative 16 times a negative 1. We can also get it by multiplying 8 times 2, or negative 8 times negative 2. We can also get it by multiplying 4 times 4, or negative 4 times negative 4. Those are all the factors of 16. So let's look at our factors of our leading coefficient. Well, that's just 1. So we can get 1 by multiplying 1 times 1, or negative 1 times negative 1. So if we put every combination of these numbers in for p, and every combination of these numbers in for q, then our possible rational zeros then would look like 16 divided by 1, negative 16 divided by 1, 8 divided by 1, a negative 8 divided by 1, a 4 divided by 1, or a negative 4 divided by 1, 2 divided by 1, or a negative 2 divided by 1, or a 1 over 1, or a negative 1 over 1. So to simplify this, we would write it as a plus or minus 16, a plus or minus 8, a plus or minus 4, a plus or minus 2, and a plus or minus 1. So this polynomial equation would have 10 possible rational zeros. Now that doesn't mean that all 10 of these numbers are solutions to this equation. It just means that the solutions to this equation will be some of these numbers. That's why these are all the possible zeros of our polynomial. So let's try this again. Our next equation has an 8 for a constant and 2 for a leading coefficient. Now all of our factors of 8, well, we can get 8 by multiplying 8 times 1, or negative 8 times negative 1. We can also get it by multiplying 4 times 2, or negative 4 times negative 2. So those are all of our factors for our p. And then our leading coefficient factors are 2 times 1, or negative 2 times negative 1. So that's going to be our q and our p over q. So all of our possible rational zeros then would be 8 over 1, a negative 8 over 1, an 8 over 2, a negative 8 over 2, a 4 over 1, or a negative 4 over 1, a 4 over 2, or a negative 4 over 2, a 1 over 1, or a negative 1 over 1, a negative 1 over 2, or a positive 1 over 2, a 2 over 1, or a negative 2 over 1, and then 2 over 2, or negative 2 over 2. Now to simplify these, 8 over 1 is just 8, so we'd have a plus or minus 8. 8 over 2 is 4, so we'd have a plus or minus 4. 4 over 1 is 4, so I already have that. 4 over 2 is 2, so we'd have a plus or minus 2. 1 over 1 is 1, so it's a plus or minus 1. We have a positive and negative 1/2, so that's a plus or minus 1/2. 2 over 1 is 2, which we already have. And 2 over 2 is 1, so we already have that one too. So, all of our possible rational zeros are plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1, or plus or minus 1/2. Now we said earlier, when we find all our rational zeros, they are all the possible rational zeros. That doesn't mean they're actually solutions for this equation. So how do we find out which ones are solutions? Well, first, let's look at this equation and find our possible rational zeros. We have a coefficient of 6 and a leading coefficient of 2. We can get 6 by multiplying 6 times 1, or 6 times a negative 1. We can also get it from 3 times 2, or a negative 3 times a negative 2. Our leading coefficient is 2, and the only way to get 2 is multiply 2 times 1, or a negative 2 times negative 1. So our possible rational zeros then would be plus or minus 6 over 1, plus or minus 6 over 2, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 2 over 1, plus or minus 2 over 2, and a plus or minus 1 over 2. So our rational zeros then would be a plus or minus 6, plus or minus 3, because 6 divided by 2 is 3. We have a 3 over 1, but we already have our 3. We have a plus or minus 3/2. Plus or minus 2 over 1 is just a plus or minus 2. 2 over 2 is a plus or minus 1, and then we have a plus or minus 1/2. So we have 12 possible rational zeros. But how do we know which ones are actually solutions for this equation equaling 0? Well, we test them individually using synthetic division. So we can pick one at random. I'm going to pick a positive 3. And if we take our equation and we divide it using synthetic division by 3, we'll see if that's a actual 0 or solution for this equation. So synthetic division, we write our coefficients. We have a 2, a negative 1, a negative 7, and a 6. 2, negative 1, negative 7, and a 6. Then the 0 we're testing goes on the outside of our division sign, so that's a 3. And then we complete our synthetic division, bring the 2 down, multiply it by 3, we get 6. Add 6 to the negative 1, that's a 5. 5 times 3 is 15. Add it to the negative 7, that is 8. 8 times 3 is 24. Add it to the 6 and we get 30. Well, if this was a solution or a rational zero for this equation, this would have come out to be a 0. So that means 3 is not a rational zero that fits this equation. So next let's check negative 3. We have our 2, our negative 1, our negative 7, and our 6. Again, we bring our 2 down. Negative 3 times 2 is a negative 6. Add that to negative 1, we got a negative 7. Negative 7 times a negative 3 is a positive 21. Add that to a negative 7, we get a 14. 14 times negative 3 is a negative 42. Add that to 6, and we get a negative 38. So this is not a 0, so negative 3 is not a solution to our equation. So we know 3 and negative 3 aren't solutions. Let's try positive 1. We have a positive 1, and then our coefficients are 2, negative 1, negative 7, and 6. We place our division sign, carry down the 2, multiply it by 1, we get 2. Add these 2, we get a positive 1. Multiply that by 1 and we get 1. Negative 7 plus 1 is a negative 6. Negative 6 times 1 is a negative 6. And 6 plus negative 6 is 0. So here we have our 0. That's what we were looking for. And that means that 1 is a rational 0 for this equation. If we plug 1 in for x here, we will find out that this equation is equal to 0. This also means that we can factor out an x minus 1 from this equation. And it's x minus 1 because remember 1 is a 0. It is a solution. So if we were to factor out this equation, we would eventually end up with a factor of x minus 1. Because if we set that to 0, we find out that x is equal to 1. Now if we think of that as a solution or a factor of x minus 1, that means that 2x cubed minus x squared minus 7x plus 6 will factor out to be an x minus 1 and then times a whole other polynomial that has these coefficients. So this would be a 2x squared plus x minus 6. Now we have this new polynomial, this 2x squared plus x minus 6, and we can plug that into our synthetic division and we can continue to test these rational zeros. So our next step would be to plug these coefficients into our synthetic division. So we'd have a 2, a 1, and a minus 6. And we would divide those by some more of these rational zeros. I'm going to pick a minus 2. And we'll test that. Now you could test this first polynomial's coefficients when you divide, because you would still find out if negative 2 or whatever you plug in is a root or a 0. But you can also use this smaller polynomial, which I think is easier, and that's why I do it this way. Now to do the synthetic division, you carry down your 2, multiply it by a negative 2 and you get a negative 4. Add the 1 and you get a negative 3. Negative 3 times negative 2 is a positive 6. Add those together and you get 0. So that means that negative 2 is also a root. That also means that x plus 2 is a factor of our equation. So that means our equation so far has broken down to an x minus 1, an x plus 2, and then here we have our remaining coefficients. This would be a 2x minus 3. So using synthetic division, we've actually factored this equation, and we're finding our rational zeros. This one told us that our rational 0 was 1. This one tells us our rational 0 is a negative 2. Now we just have to solve this one. Well, 2x minus 3 equal to 0. If we add 3 to both sides, we get 2x is equal to 3. Divide by 2, and x is equal to 3 halves. So then our three rational zeros then are x is equal to 1, a negative 2, and 3 halves. Now the next thing we have to talk about is Descartes' rule of signs. If we have a polynomial written in standard form, then the number of positive real solutions is the number of sign changes in the equation, or less by an even number. And the number of negative real solutions is the number of sign changes in the equation f of negative x, or less by a real number. Now f of negative x is just plugging in negative x for x in our polynomial. So let's try this. Here we're given the polynomial f of x is equal to 2x to the 5th minus 3x to the 4th plus 5x cubed plus 12x squared minus x minus 13. And then here we're given the exact same polynomial, but they've just substituted in negative x for us. Well, let's look at our first one and determine how many sign changes we have. Well, here we start with a positive 2. And then we go to a negative 3, so that's one sign change. From a negative 3, we go to a positive 5, so that's our second sign change. From a positive 5 to a positive 12, those have the same sign. a positive 12 to a negative x, that's a sign change. And then negative x to a negative 13, those are the same sign, so that's not a sign change. So we're looking at the positive version of our polynomial, and we have 3 sign changes. That means our solutions will consist of either 3 real numbers, positive real numbers, or less by an even number, so 1 real solution. Now let's look at the negative version. If we simplify this, negative x to the 5th is a negative x to the 5th. So then this would become a negative 2x to the 5th. A negative x to the 4th is just x to the 4th. The 4th gets rid of our negative. So this becomes a negative 3x to the 4th. A negative x cubed is a negative x cubed. So multiply that by 5 and we get a minus 5x cubed. And negative x squared is just x squared. So multiply that by 12 and you have a positive 12x squared. Minus a minus x is a positive x. And then we have a minus 13. So now that we've solved that or simplified it, let's count our sign changes. We have a negative 2 and a negative 3. Those are the same sign. Then we go to a negative 5. Again, that's the same sign. But from a negative 5 to a positive 12, we have 1 sign change. From a positive 12 to a positive x, those are the same sign, so that's not a sign change. Then a positive x to a negative 13, that would be our second sign change. So, counting those with the negative version of our polynomial, we find out that this original polynomial can have either 2 or less than by an even number, so 0. So it'll have either 2 or 0 real solutions. Now there's 3 possible types of solutions. We can have a positive real solution, we can have a negative real solution, or we can have a solution that's not real at all. So it's imaginary. Well, if we have 3 or 1 positive solutions, and we have 2 or 0 negative real solutions, so we have a 2 or 0, we have to think of all the combinations of solutions we can have. Here we have a 5th power, which means we're going to have 5 solutions. So if we have 3 positive real and 2 negative real, that means we'll have 0 imaginary. If we have 3 positive real and 0 negative real, well, that means we have 2 solutions still to find, so we'll have 2 imaginary solutions. If we only end up with 1 positive real and 2 negative, well, that's only 3 solutions so far, and we need 5, so again we'd have 2 imaginary. And if we only had 1 positive real and 0 negative, then we could have 4 imaginary solutions. Now Descartes hasn't given us any of the solutions for our polynomial. The rule just gives us hints of what our solutions should look like.